Mr. Kuldeep Singh, and he is a research scholar here. He's working with the power electronics part for plug-in vehicles. Okay, so I think he is one of a good expert, and he's really a brilliant student here. So I think his lecture will be one of the best lecture in this whole course, I can say. And he will be just covering the power electronics part involved in plug-in vehicles, and he will be giving you, and you can just, he will also discuss what are the research scopes in this area, since he has not fully completed. So I also know the limitations what he has, because he cannot give many of his work, but still he will be giving you an insight on where are the research available in this area, and what is plug-in vehicle, because now you all know one of the lecture you have heard on smart grid. So smart grid, the main portion, plug-in vehicle also plays a very important role in this smart grid. So I think this will be one of the good lecture, and I hand over the session to Kuldeep.
Thank you, ma'am. So we are starting with the power electronics for plug-in vehicles. But before we start it, let's say about you have discussed smart grid, right? So in the smart grid, you have discussed about the various generating station, yes, distributed generation, right? In that they are providing the power to the commercial sectors. But in the commercial sector and in the domestic sectors, they are also using vehicles nowadays. And the EVs and the HEVs we are using, they are like another source of power, because we are not considering them as a power, we are considering them as an electrical load. But what if we want to use those electric vehicles as a power source also? That is my research topic. Okay, so first of all, what is energy? Energy is the basic need of all living entity. We already know that. So there are three types of energy sources. One is the non-renewable energy resources, which we already know, that is coal, natural gas, diesel, and nuclear. And another one is renewable energy sources, that is, we also know solar, wind, hydro, fuel cell, and then there is an alternative source of energy, that is battery, electric vehicles, and hybrid electric vehicles. Nowadays, we are using batteries as a regulating system, regulate our DC voltage link. Okay, so if we want to use as a power source, then what we have to do? We will discuss in this. So further, the problem associated with the our conventional energy sources, they are using, they are actually continuous increase in power demand we are facing right now. So in the continuous increase of power demand, we are also increasing our power generation. So for that, our depletion of natural resources is increasing very fast. They have very low conversion efficiency, because we already know in the thermal, in the hydel also the efficiency is about 45% to 50% maximum. So, and they are also very less reliable, because they can't give you power continuously. At some time you have seen the breakout in 2012, where 2 days there was no electricity. That is because of the increase in power demand at one line, and therefore all the generating station were blackout. So you have already discussed this part, the smart grid. In this we have generating stations and transmission system and distribution and consumption. As you can see, there are electric vehicles in the, at this point electric vehicles are there, but they are using as a load. So in this period we are going to discuss about what are the power electronics present in the electric vehicle systems, and we are also going to see what are the various other components that are present in the electric vehicle system. So EVs are considered as the future cars, as we already know, because we are depleting our natural resources like fossil fuel, petroleum products. So we are going for the EVs and HEVs. They uses one or more electric motor or traction motor for propulsion, and they can be powered through a collector system by electricity from off vehicle sources. That means our natural energy resources, like grid. Okay, then self-contained with a battery and the solar panel or a generator to convert fuel to electricity. They can also use their uh, roof panels, solar panel we are there. We can also use that thing over a car. So when the car at standstill, and that means in the parking lot, or when you're working from 9 to 5, so your car is parked at the parking lot, so it is not generating anything right at that point. So if we have a solar panel or a generator at the rooftop of a car, then that car can produce electricity at continuous rate. So we can use that thing as a generating alternating power also. So first of all, what is for the modeling of electric vehicles? Electric vehicle exhibit three main challenges. That is, has a limited driving range. Second is a long charging time, and third one is high cost. And all these three component related to the batteries. Because if you have a higher battery source which can provide more power, it can go for the limited driving range will not be there. Then charging and discharging time of a battery, this is also part of the problem. And high cost is only due to our battery sources, because as you can see, if we are using, for example, we are using hybrid electric vehicles. In hybrid electric vehicles there are four types of hybrid electric vehicles. First one is parallel type, second one is series type, then is power split type, and then is plug-in type. So if we are using a parallel type, in that we are using less battery sources in the car, and that battery sources along with the internal combustion engine, they are working parallelly. Okay, and they're providing the power to the our drivetrain system. But in the series type, what is happening is the moment the battery sources stop giving power to the electric generator or motor system, the IC combustion engine will start giving power to the battery sources. So they charge the battery, and then again battery will give power to the drivetrain system. So that is happening in the series type. For that, we need an extra bulky amount of batteries in the series hybrid type. So that's why series hybrid is most costlier than other type of hybrid electric vehicles. So modeling of EVs are done in order to estimate its energy consumption, how much energy it is consumed, and model are developed only for that part. Then modeling of EV consists of three, so these complex components. There is a transmission system, that means power given to the wheels. Then electric machine, which type of electric motor you're going to use. Then power electronics component like DC to DC chopper circuit, inverter circuit, rectifier circuit, and then there are batteries. So let's see. In the modeling architecture, as you can see, this thing consists of a fuel cell, supercapacitor, and batteries. Right? These are the power sources for our electric vehicles. And then these power sources are giving their power to the DC-DC chopper circuit. Right? And then all the three systems are providing a continuous voltage, a constant voltage at DC link, and that DC link is providing DC voltage to our inverter circuit, DC to AC, and then DC to AC circuit is giving power to our electrical motors. And electrical motor we are going to consider are going to be three main types. This is another one of model architecture in which we can see that there is a grid system. Through the grid system, the rectifier is providing a DC voltage, which we're going to boost up and given to the battery sources. And the battery sources are giving their voltage to the inverter circuit, and inverter circuit is giving power to the electrical machine system. So as you can see, there is a system of from grid to transmission system of electrical vehicles, as you can see. So power electronics in electric vehicles. There are mainly four main types. Energy sources and storages, that are batteries, fuel cell, and supercapacitor, as you have seen in this system. Okay, this whole system we are considering inside the circuit. This whole part is of power electronics component. And then there is a traction motors that we are using, soft switching inverters, and DC to DC converters. Energy sources and storages. There are basically of four main types. Lead acid batteries. All right, as you have seen in our phones also, we are using lead acid batteries. In our car, we are using lead acid batteries. Then there are nickel metal hydride batteries, lithium ion batteries, and last one is the fuel cell. Fuel cell, you guys already know. Has anybody told you fuel cell? What is a fuel cell? All right, we're going to discuss that part also. So in the fuel cell, basically, we have hydrogen and we have oxygen. We're trying to mix those things and try to generate electricity. And in that we are producing water. So there is no harm in that. Okay. So a fuel cell is a system in which we use hydrogen and oxygen and mix it up. And that hydrogen produce electrons in order to, because as you already know, H2, if we mm, if we divide it into H negative, H positive, so it has to deliver electrons. Okay, it deliver electrons, and in order to O2, O2 needs electrons. All right. So what it will do? It will take electrons from hydrogen, and then what it do? We can make a circuit where hydrogen provide electrons to oxygen plate, and then in that process it produces current. All right, and ions will pass through a solution, and that solution will make water. Will try to make as a catalyst. They will try to make as a water. In the last point I have wrote, electric vehicles use deep charge discharge type valve regulated lead acid batteries. But we are now going for nickel metal hydride batteries also. All right, because these are the battery sources we are not going to cover in this topic, because these are not of power electronics part, not in power electronics part. So if you are going to develop a basic model of batteries, this is how you're going to make it. A VBAT Intel cell, this it's a cell or lead acid batteries or any type of battery. So what it will do, we have a diode circuit along with the resistive circuit. Because the current will flow, it will provide a resistance also. So the amount of power that should be delivered by the batteries may not be constant, and it also depend upon the time. All right, at 1 hour it will give less voltage, at 2 hour it will give more less voltage. So the resistance will provide the same circuit, the same concept, that our batteries have reduced their power voltages or voltages at the end of some time. Then there is a traction motors. There are basically three types of traction motors. One is induction motors. As you have already know, most of the industries are using induction motors. Then there are permanent magnet motors, in which we have PMSM motors and PMBLDCM motors. PMSM is permanent magnet synchronous motor, and PMBLDC motor, BLDC motor means brushless DC motors. Basically, we consider BLDC motor as a DC motor, but it's not. It's a synchronous motor actually. Okay, but in BLDC motor, we have to excite it with the trapezoidal waveform. The voltage will be of trapezoidal type rather than a sinusoidal type. In synchronous motor, we excite it with the synchronous, like as you have seen in the field winding, we provide voltage in the synchronous motor. All right, we provide it with the sinusoidal type. Waveform will be sinusoidal type. But in the case of BLDC motor, it should be of trapezoidal type. Right. And there can be a combination of these motors also, like in the motor generation set is also right there, motor alternator, like. All right. In this case, the PMSM provides high power density and high efficiency. So basically we use PMSM motors for our electric vehicles. Okay, but nowadays we are going for BLDC motors also, because it provides more control. So I'm going to discuss modeling of PMSM, because my MTech project was on PMSM drives, so I can better explain you that part. Okay, the electric machine in the PMSM part is divided into two parts: the electrical part and the mechanical part. The electrical part consists of, like, we have three-phase voltage, right? What we want is we convert this three-phase voltage into two-phase system, like DQ reference frame. So in this, first of all, the voltage equation is there, where a DQ reference frame is we have created using a three-phase voltage VABC, right? And this matrix is known as Sparks transformation matrix. Okay, when you read about electric drives, you can see that when we are making try to make a model for any electric drives for three-phase system, we try to convert this three-phase system into two-phase system, okay, and then into single-phase system. By making it into a single-phase system, we were trying to make that a whole electric motor, which is of alternator type, into a DC motor type, because as we have known that electric motor, we can control its torque and speed, right, by controlling its current, field current and armature current. Similarly, we are trying to do the same thing here. We're trying to make this three-phase system into a system which is compatible with the DC motor. So here we are converting this into a DQ reference frame. Like in the same case, armature current and direct field current. In the case of DC motor, we are making direct voltage or direct current or quadrature axis current or voltage. So this is the first step. Then similarly, the flux produced by the same system is also converting into direct axis type and quadrature axis type. So these are the basically the governing equation to develop the simulation model for PMSM system. At the end of the day, I am going to show you how the model is developed for the PMSM system. Because if you can't make the PMSM system model, we can't develop EV models. Okay. Then there is a winding current equation in which we have say, as you have seen, we have developed IQ and ID equations. Okay. These are the basic equations for VQ and VD. These are come from these equations. And then there is a rotor motor equation in which torque and speed we will get. And as you have all seen, the current equation or the voltage equation will consist of differential equations and integral equation, right? Because if we want to develop any model in the mathematical model in the simulation in the Simulink, we need its governing equation, or you can say its differential equation or integral equation. Because if we have this equation, we can easily make our PMSM model, any model actually. So those are the rotor motor equation for PMSM system, torque and speed. And these are the mechanical part of PMSM system, in which the electrical torque developed by the motor should provide the torque to the shaft, that is TS, and the TC is the conversion process torque, and then there is inertia provided by the our shaft. The moving shaft is also providing an inertia, and also there is a frictional viscous, that is BV, which are provided by our shaft. So this is the mechanical part of the PMSM system, and PS is the power delivered to the shaft, that is PS. So if we all make this PMSM system, as you can see, there is a VA, VB, VC. This is a Simulink model. This is a VA, VB, VC, that is the power coming from our grid. This VA, VB, VC is converted into VD and VQ, like two-phase system, and then this power is delivered to the our PMSM internal structure, in which we have developed IDO and IQ, ID and IQ, and also electrical torque developed by the motor, and also the speed of the electrical motor along with theta. Okay, and then these ID and IQ will help us in making current IABC. Okay, most of the time, if we want to control our PMSM model, like in our electrical vehicle, we also want to control our power of our PMSM system or any drive. So in that case, we develop a control strategy. In that control strategy, we actually either we use the voltage equations or either we use the current. So here what we have done is, because uh, our control strategy need ID and IQ star, that is the reference current. Because what we are doing is, in order to control a PMSM model, either what do you want to do? I want my PM our vehicle should be running at 50 kilometer per hour or 60 kilometer per hour. So what you will do, either you throttle less or you throttle more. All right, that is the reference. We convert this reference point into a current model. Okay, this id current will be if the id current will be this much, the motor will provide this much power or this much throttle, and if the iq current is this much, it will provide this much power or throttle, right? So similarly, for that we need an IABC system. This IABC system will convert into IDLQ model, and this will provide a control strategy to control the power that we delivered by our PMSM system. Now, in order to obtain the VA, VB, VC, that is three-phase voltage, right? So, in order to get that, we need an inverter circuit because our electric vehicle consists of batteries. So, that battery should provide power, three-phase power. So, we are converting this DC voltage into three-phase AC using inverter circuit. And the most important part in the inverter circuit, it must possess low switching power losses. Okay, as you can see, low switching power losses, because if the switching power losses is very high, so then there is no point in using the power electron devices. All right, so therefore short switching inverters are generally used in electric vehicle rather than hard switching. When we are talking about short switching, and that means we are not going for abrupt change in voltage or current, right? If you switch on our device like an inverter circuit, if you there's a switching device, if you turn it on, then there will be a switching patterns there, right? There will be transition. But we want the transition will be very slow. We don't want that the current or voltage will jump very high, or maximum overshoot should not be there. So in that case we go for short switching inverters. So short switching inverters are also of two types, that is zero voltage transition and zero current transition inverters. This is a normal inverter circuit in which there is a single battery source V bat, the voltage given by the battery source, and then this battery source will give power to our all these six devices. As you can see, the QA is a switch and DA is the opposite diode that is connected to our switch. So as you can see in all this, the switching losses we're going to calculate in this case. What is the switching losses in QA? What is the switching losses in DA? If you can calculate the switching losses in that, then you can develop these equations, which is given by a scientist in 2005. That these are the losses that should be occurring in our PMSM in our inverter circuit. Okay, and the total losses will be how much? Six times, because how much switches we are using? Six switches and six diodes are there, so they will be of six times the amount of losses that is present in our inverter circuit. And this will be the input power and efficiency. The power input is V, that is voltage that is provided by the battery, and the current is that is provided by the inverter circuit, that is coming current flowing in the inverter circuit. We should provide the power to the electrical motors and also to its losses. So this will be the total input power of our inverter circuit, and the efficiency will be, if the electrical motor power is positive, that means it needs power. Okay, it is acting as a load. So at that time our efficiency will be considered as the electric motor, that is PEM will be the output and P inverter will be the input. But when our electric motor will be working as a generator set, like regenerative braking we have heard of, that when the our AC motors will work as a generator, so at that time they are providing power to the our DC model, right? Or they're charging to the battery. So at that time, the PEM will be negative because it is delivering its power back to the battery system. At that point, our efficiency will be P inverter will be considered as the power needed by the inverter circuit, and PEM is the power who is delivering the power. A zero voltage transition inverter will something look like this. So in all these cases, we are going to discuss that the switches we are using is also there are six switches we are using along with six diodes in this case also and also in this case, but in this case we are using a zero current transition inverters. So if we are going for turn on and turn off time, at that point at the time of turn on the current jumps off, as you can see, because voltage is providing to the inverter circuit. When the switch is on, the voltage will come down to zero and the current will jump to its maximum point. But it will, because we are going for source switching, at that point the losses will be very less because the current will not jump high immediately. It will take some time. Next is the DC to DC converter circuit. This converter circuit will provide constant DC supply to the inverters from the batteries, and it need battery to charge the DC bus for the initial startup power. Okay, when the motor is starting or you want to start your electric vehicle, at that point you need a DC power. For that you need a provide power to the DC bus, like as you have seen in this case. The DC link is like a DC bus. Okay, so the chopper circuit is needed, like in this case the chopper circuit, that this DC to DC is needed to provide the initial power to the DC link so that it can provide power to our inverter circuit, which will eventually run the our PMSM electrical motor. Now it also need to keep batteries charged, because if we are making our electrical motor to go for regenerative braking, that means it's going to provide their power to our battery sources. But battery source is not of very high voltage, because inverter circuit or electric motor will run at 110 volt or 210 volt, or three phase it is 440 volt, right? It if it deliver power at the same rate, that means it will going to deliver the power, or it will delivering the voltage about 110 volt to 120 volt when the power conversion again take place. Okay, so but our batteries of is only of 24 volt or 12 volt or 48 volt. So at that time we need the buck converter. All right, so rather than going for buck converter or boost converter, we go for buck boost converter. Okay, if we are not going for regenerative braking, we only need boost converter at that point, right? But if we're going for regenerative braking, then we have to go for buck boost converter. This is a non-isolated type boost converter. In this, as you can see, if the voltage is provided when the switch is on, like in the center part, when this switch is on, all right, this voltage source is delivering its power to the inductor circuit. All right, but it will not give this power will not be delivered to the capacitor circuit, because at that point this is short circuited, switch is short circuited, so it will not give power to our capacitor circuit. So that's why when the gate is on, inductor charge and capacitor will discharge through resistor. Okay, but at the same point when the this switch is off, that means the power of this voltage source and also of inductive power will not be delivered to the capacitor. So the capacitor will charge to the more voltage than the voltage delivered by the battery source. That means it's boosting its voltage. So that's the main concept. And as you can see in the average output voltage, V is given by 1 upon 1 minus d Vg, and d is the duty cycle. Okay, d is the duty cycle. This is isolated boost type converter. This is non-isolated, in which this is present in the internal circuit of our EV system, and this is isolated boost converter. The isolated boost converter we use is actually when we are using our grid system types plug-in. Actually, if we want power from grid system, then we have give that power to our battery to charge it. At that time we need an isolated boost converter at that point. So this is the system for boost converter where we are making isolation to our secondary circuit, that is V, this circuit. Okay, as you can see here, the constant voltage will be there, VG will provide, and that will provide single phase AC voltage. Then the isolation system will be there, and then we have rectifier which will provide constant DC voltage. So there are two types of system: isolated and non-isolated boost type converter. This is all done to make our circuit safer. Okay, if there is a problem at the motor side, then that problem should not be occurred in the our battery side. All right, that's why we go for isolated boost type converter. This is a buck boost type converter. Okay, as you can see in the buck boost type, this whole circuit switch is provided at this point. When the switch is on, all right, it will provide its power to inductive circuit. Okay, inductive circuit will charge at that point. Capacitor is nothing there. There will be no charge, so there will be nothing there. So at the moment this switch is off, right, the inductor will provide its power to capacitor circuit. Okay, and the voltage at that point will be negative, and the output voltage at this point is V naught equal to D upon 1 minus D. Okay, it can either provide boost voltage or either provide buck voltage depending upon the duty ratio of duty cycle of our switch. If the duty cycle is more than 0.5, then it will boost up. If it is less than 0.5, it will buck it. So now we are going to check for the model that will be developed for PMSM model. Right? We're going to check for PMSM model. This is how it generally looks like, the PMSM model. Okay, VA, VB, VC as a three sinusoidal voltage will be there, and it is providing power to our DQ reference frame. That means this system. If we double click it, as you can see, these are equations are there. If you want to check if these equations are right or wrong, you can see in the presentation. The VD, VQ and VD, right? This is 2 by 3 times VA cos theta R plus 2 by 3 times VB into cos theta R minus 2 pi by 3 and plus 2 by 3 times VC cos theta R plus 2 by 3. If you make a method, solve it, then you will see there is a cos theta R here, sin theta R here, VA, VB, VC is there. We connected it to the mux, so it will provide only a single line. And then if we control it, here is U1 is describing VA, U2 is describing VB, and U3 is describing VC. Okay, and similar. And if we use this whole system, we can see that it will develop a VQR or VDR. Okay, it is all about DQ model that is we are using in the PQ transformation. If we want to see, then you have to solve it first. Okay, then this VQR and VDR is delivering its power to our main PMSM DQ model, motor model. In this, as you can see, there is a VQ model and there is a VD model. If in subsystem 2, we are again there are more equation which is providing equation like psi q psi mq, and iq. Okay, these are the fluxes developed by the our iq. Okay, psi q is the flux produced by current iq, and psi mq is also the flux produced by our iq, and iq is the actual current. Similarly, there is a subsystem model of this here, in which they, as you can see, vd is providing psi d, psi md, id, or psi lkd. The iplkd is actually losses that are present in the our inductive circuit that is provided by our windings. Okay, so as you can see here, we are using 1 by s, right? 1 by s is integration in our yes, integration. So as we have seen in this diagram, lambda d is a equation that is we are using it as id, and id is equal to ld into id plus lambda f, that is the field, magnetic field, and lambda q is also the function of lq and iq. So basically these are the natural governing equation, but there are not only these these are only very less amount of governing equation, only normal governing equation. But if we want to develop a whole full PMSM system like this one, there is actually around 48 to 49 equations. And if you combine these 48 to 49 equations, then you can develop this kind of model. What I want to show you in this case is using just normal equations that is provided by our books, because they provide equations, not whole circuit for the motor, right? So using only the mathematical model of that equation, we can make our whole system PMSM model. So this whole system is developed on the basis of only those equations. If you want to see how it's actually look like, this is how it actually look like. It's a whole system in which VA, VB, VC will be there, converted into VQ, VDS or V0, delivered to VQ and VD. Okay, given this power to our motor system. Actually, I have just opened all the subsystems that are present previously before. Okay, it, it's so much complex, so that's why I have to make it as a system. So as you can see in this, these are just normal equations. Okay, no more, no actually electric motors are used, no voltages like batteries are used, just equations. Okay, and this, as you can see in this three-phase PWM inverter, we are using a universal bridge. In the case of universal bridge, is also using 6 switching devices. Okay, so we need a 6 pulses to control this universal bridge. And this universal bridge is connected to an RLC branch or resistive branch, which will provide the voltages, three-phase voltage. So we are going to see what kind of voltage is coming and what is the gate pulse required for this system. This is a system for gate pulses in order to switch over universal bridge. In this, we have a repeating sequence that is for other type. In PWM cases, we are using pulse width like triangular type waves, and we combine it with our sinusoidal AC waveforms, and then it will provide 6 switching pulses like in this system, this mux. Okay, and this, as you can see in this, when there is more than equal to, if it is not, then there is another pulse. If triangular pulse is more than sine wave, then what? And if it is not, then again another pulse. So at the same way, we are getting 3 pulses from this system, and we are providing this 6 pulses to our IGBT system. If system whole, this type of waveform we are getting. Okay, it's a three-phase system, sinusoidal type, Okay, an alternating type, but it's not completely sinusoidal. That's the main problem we have associated with our normal inverter circuit. They will never provide a sinusoidal AC supply. So for that we need the filter circuit. Okay, so this is a system for our three-phase inverter circuit. Let's see more of them if we have even filter circuit also. Okay, this is a system. Repeating sequence are there given to our universal bridge, and the universal bridge is again connected to another subsystem which is a filter circuit. This filter circuit will consist of inductive or capacitive branches like this one. Okay, if you control this RLC, you will control the waveform, you will control the design of a waveform. So if we run this situation, this model, run it again. There's a problem with something in this. Okay, there's some problem with the filter circuit, so I will show you that in another lecture. Now this is another circuit, okay, in which as you heard of the word multi-level, right? Multi-level inverter. So this is also a multi-level inverter circuit in which we are using, this is a 5-level type multi-level inverter in which we are using a cascaded H-bridge type multi-level inverter configuration. So for 5-level type, for each level, as you can see, there are 8 switches we are using. If you want, and one full bridge inverter is there. One full bridge inverter will provide you 3 level. Okay. Then if you add another one, you will get 5. If you add another one, you will get 7. As you keep on adding, you will increase your multi-level inverter levels. Okay. So this is a 5 level type. So in this we are using 2 full bridge inverters which utilize 8 switches. And for those 8 switches, we are controlling this by our triggering generator circuit, as you have seen there. Okay, this is the most simplest way to develop a multi-level inverter circuit. And this, as you all can see, if you run this program, as you can see, the number of levels have increases. At that point of time, in the previous example, as you have seen, there is after 0, there is 1 level, and after 0, there is -1 level. In this case, there are actually 2 level above 0 and 2 level below 0. Okay, so it's a 5 level type. So, as if you see amount, it's more look like sinusoidal, but it's not completely sinusoidal. So if you keep on increasing the levels, it will more reach up to the sinusoidal point. Okay, but it will never be a sinusoidal. It will be a step type. Okay? Step type sinusoidal waveform. So for that, if you keep on increasing the level, you more accurately reach at sinusoidal waveform. But at that point of time, if you need a filter circuit, that filter circuit cost will be very less, because at that point of time, the harmonics present in the sinusoidal circuit will be of more than 11th or 13th. Okay, but if you're using only simple type, they will be, then as you can see, there will be more harmonics present in the circuit. If you want to see the number of harmonics present in this circuit, okay, so let's see number of harmonics present in this circuit. So if you want to develop any power electronic circuit in SimScape, you need a power GUI. Power GUI, this power GUI. Okay, because in SimScape, the number of components present in the power electronics in the SimScape, they need another source to run the program or run that model. For that, you need a power GUI. Okay, if you go this, as you can see in this square box browser. Okay, if you open up a library browser, so what is the use of power GUI? The power GUI will help you to run the power electronics devices that is present in the Simulink model. Like you're using switching devices, right? So in order to run that device, we need a power GUI. Okay. But there is no connection, sir. No, there is no need of a connection. It's like they are giving the power to the GUI, our switching circuit, that you can work now. Okay. जैसे हमारे हमारे इसमें भी है ना, भगवान का हाथ दिखता तो है नहीं, वही चीज है यहाँ पे भी, ये पावर जी है, वही चीज है जो सिंपल इन्वर्टर थे घर में हम लगाते हैं, उस पे लिखा होता है 20 मेगाहर्ट्ज टेक्नोलॉजी, 20 किलोहर्ट्ज टेक्नोलॉजी, 20 किलोहर्ट्ज। हाँ, दे आर यूजिंग द स्विचिंग डिवाइसेस टेक्नोलॉजी ना, कितने उसके स्विचिंग हो रही है उस टाइम पे, 20 किलोहर्ट्ज की है, 50 किलोहर्ट्ज की है, 20 किलोहर्ट्ज, आई नेवर हर्ड दैट।
देखो आउटपुट तो आपको 50 हर्ट्ज आती है
50 हर्ट्ज है
लेकिन बहुत सारे बॉक्स के ऊपर आपको 10 किलो हर्ट्ज 5 किलो हर्ट्ज 20 किलो हर्ट्ज टेक्नोलॉजी लिखा होता है
Switching frequency कह सकते हैं.
that will be switching frequency because 50 hertz is the normal supply power but if we are using they are that will they will be using a switching circuit of 5000 or 10,000 or 20,000 yeah
वो क्या है
that is let me tell you
that is the first basic initial level of
you see I have set the triangular generator frequency at 1000 right because if you increase this frequency the number of times the sinusoidal frequency will compare it with this switching frequency that means that we are talking about the reference sinusoidal right because what we need a sinusoidal right sinusoidal voltage we need at the output of that will be our reference okay we want to compare we will compare it with what this switching frequency triangular type. So what it will do, the more number of time it compare it with our sinusoidal type, the more it will reach up to its accurate level. Because switching will be done at what point? Let's say ki my voltage is 20, I need 30. At that point, I need a switching. Okay, but my waveform of my frequency of this switching pattern is less. So at the point I need 30, it will not compare it at that point.
If it is one, it means that is a pure scale. One time on and then off.
Yes.
Two is there, then two scales are in between.
Two scales, yes. Compare it will compare it with two and then give its switching command to our switches. So right now it is comparing it.
Means that sinusoidal wave basically overriding upon this 1000.
Yes. No. Let me show you what is happening up here. This is like the circuit of a switching circuit, okay, which is providing switching to our switches, power electronic switches. In this case, there are levels. Let's say this is a carrier frequency triangular waveform. This is a carrier frequency triangular waveform. How many are there? Four are there. Okay. Then there is a reference sinusoidal voltage. Right?
एक तरह से मॉड्यूलेशन हो रहा है
ये मॉड्यूलेशन हो रही है ठीक है ना that 20,000 that 10,000 those are modulations ठीक है
and the more switching frequency is required because for this because of the less power dissipation
yes
cycle. So if 1 upon 50 times that one switch is on, it means more power dissipation is there. And number of times means on and off, on and off, on and off, on and off.
गैप्स छोटे हो जाएंगे because if we see a DC voltage battery is there right if a longer time that thing will on switch will be on it will provide DC voltage
15 किलो वेट उठा के रखो 5 मिनट तक वो नहीं उठाया जाएगा वही करेगा उठाते रहो रखते रहो
I have seen in my city where I'm working the electric vehicles are there they called them as a ground वो क्या करते हैं they are meant for the capacity of 3 to 4 persons
yes
regularly the operators take the 7%, 8%, 9%. And after 1 year the life of the battery get totally destroyed
because the amount of
replacement.
yes it needs the replacement because the number of charging and discharging will be very high because if they are saying that only 3 to 4 people should go there the amount of weight that a battery can operate over yes that's the main problem so here is what's happening is there at the point you can see this triangular waveform is touching this sinusoidal waveform at the point it's touching it is the program is operating that if it is more then switch on if it is less then switch off okay so every time if more number of this is there then number of switching will be more but we can't go for more than 5,000 or 10,000 because after that point there will be more switching losses so we have to limit our switching losses So this is a three-phase VSI cascaded inverter. We call it as cascaded inverter because we are using a simple single-phase bridge inverter in cascaded form. If you this is a 5 level type, if you want to make it level 7, add another one. Okay, make it 9, add another one. Like if you, in this case, I have shown you there are. Let me show. In this case, as you've seen, for single phase there is only two inverter bridge, right? What if we go for 9 level inverter? This is also 5 level type. This is a 9 level inverter. Okay, for each phase are divided into the gate pulses are divided into three phases. For each phase, these are the pulse controlling pulses or gate pulses that will be provided to the inverter circuit. This is an inverter circuit. Okay, for each each phase. Now, if we double click this, as you can see, a normal universal bridge is a normal bridge type inverter. Okay, so in the case of 9 level inverter, I have told you for one universal bridge will provide 3 level, so 4 will provide 9 level. So if we want to check that if our circuit is correct, just run it because I already know it's running. This is how it looks like. Now the center point is 0 is there, right? Then how many levels are there? 1, 2, 3, and 4 above, and 4 below, and 0 is the ninth, right? So as we have increased our universal bridge in the circuit, our levels are also increasing with respect to increasing our universal bridges. So this is the most simplest way to develop a cascaded type H bridge multi-level inverter. Okay, but nowadays people are working over reducing the number of switches for this circuit because a normal 9 level type inverter circuit required how much for 9 level? Yes,
6 times.
right. So if we are talking about 11 level, that means 60 switches are required, total number of switches. Okay, though people are working over reducing these switches up to 20 or 10. Okay, even the 7 level, 9 level type are required only 5 switches rather than 20. Okay, so people are working over this circuit, this point at this stages also. So this is a multi-layer inverter type structure as I think it will be good enough for today, right? Because if because for this circuit you should know about MATLAB first, and then there is a book. If I want to recommend, it will be Shailendra Jain. Modeling and simulation, modeling and simulation using MATLAB Simulink. I think yes. Shailendra Jain sir ki hai. So I think that book has provided very much basic knowledge of everything. All the power electronic circuit, that means inverter circuit or AC to AC controller circuit, DC to DC rectifier circuit, in not only in Simulink but also in MATLAB script files also. He had developed all that, and he has shown good example. So if you follow that book, I think in 1 month you will able to grasp every knowledge of about the MATLAB and how to develop even the mathematical modeling of these circuits. Okay, in if you want to develop like modeling of electric drives like PMSM or induction motor or any other motor, there are actually two books which are very good for it. So the one name is CM Onge by CM Onge, dynamic simulation of electric motors, or I think electric drives. Actually, that's the best book because it's also providing its MATLAB examples.